Hello everyone, my name is Ofir, and today I'm going to present you our work, a collaboration with Reichman University, Tel Aviv University, IBM, and Berkeley. The work is PromptonomyViT, multitask prompt learning, improves video transformer using synthetic scene data. High-level motivation. So, video understanding has always been widely explored. As of today, more and more video and data is captured and it becomes huge amounts, growing exponentially. However, modern methods are far from perfect and there is still a lot to be done. We propose a novel method for fine-tuning transformer-based video models. Scene-level information, both spatial and temporal, is often crucial for solving high-level video tasks such as action recognition. Collecting and annotating video dataset is costly and time-consuming. As time goes on, synthetic data becomes more and more popular, more realistic, more higher quality, and accessible. In this work, we exploit these facts and propose PVIT architecture, which I will elaborate soon. Video transformers have become very popular and there's a lot of works coming out every day. For example, some of them are mentioned here in the slide: MVIT, multi-scale VIT, motion former, times former, and so on. Each one proposes its own mechanism, architecture to process the video, usually followed by different attention approaches. For example, times former does divided space and time, which applies two separate independent attention layers. Motion former tries to learn trajectories between slides, between frames, and so on. These architectures are very general and they are very dynamic, and our work is based on such concept. The concept of prompt tuning was originally proposed by Google in the NLP domain. They proposed to add learnable tokens while keeping the pre-trained LLM frozen. This enabled them to fine-tune the model in a very efficient way, and they also showed some improvement in NLP benchmarks by training only tens of thousands of parameters instead of billions. Later, the second paper in the slide was the first to address the vision domain. They applied similar concept but on image datasets. As well as the first, they showed some improvement, but they didn't report on famous benchmarks such as ImageNet. Other methods, like the third one in the slide, propose multitask prompt tuning on images, but most of them, when we refer to multitask, use multi-label datasets, which are extremely rare when we go to the vision domain. Our contributions. As mentioned, leveraging synthetic data is a challenge, and also real video datasets are lack of multi-annotation and scene-level annotations. We propose to combine multitask learning with prompt learning. In PVIT, therefore, each prompt is responsible for some auxiliary task. It can be applied to any video transformer based as being general and invariant to a sequence length. The intuition behind our method can be seen as the follows. The task prompts can be seen as some kind of streams of information. Each prompt is responsible for extracting the correct and essential information in order to predict and solve his task, whether if it's depth estimation or normal estimation or segmentation and so on. These prompts are responsible, as mentioned, each for its task, and therefore we name this concept as promptonomy. Our method can be described in this figure, where on the left side the collection of synthetic dataset with their corresponding scene level annotation are optimized. For example, depth estimation, normal estimation, semantic segmentation, and so on, while on the right we optimize the downstream dataset, which is a real video dataset with a high-level task, for example, action recognition. All these are trained together in a multitask manner with our prompt learning method. Diving deeper into the architecture, it can be seen that at each training step, we sample randomly from our synthetic dataset pool together with their corresponding annotation and optimize according to them. For every task, we define a task objective, and each output prompt is fed into its corresponding head for prediction. If for a given step some task is not available, then it will not be optimized. In the following figure, it can be seen that the task prompts produce meaningful maps despite not receiving such labels for real videos. This implies that the model, even though optimized for specific tasks from synthetic data, it still can produce some meaningful information on the downstream dataset. Results. We report consistent improvements on the following tasks and benchmarks. Something else for compositional and few-shot action recognition, something V2 for action recognition, Ego 4D temporal action localization and point of no return classification, EVA 2.2 for action detection, and Diving 48 for action recognition. In all our experiments, we use the MVIT v2 architecture and apply the MVIT approach upon it. It can be seen in this slide that on compositional action recognition on something else dataset, we report an improvement of 2.2 over previous methods, and on the something v2 with action recognition task, we report a boost of 1.2 on the top one accuracy. Similarly, we report a significant improvement on the Diving 48 dataset and the AVA 2.2 dataset, which outperforms all previous works and also our mentioned baselines. Following to that, we define various baselines and model variants in order to show the significance of our approach. I will not elaborate about it here, but it can be found on the main paper. We also perform some ablation studies, seeing each auxiliary task, how each auxiliary task helps different datasets. We also perform ablation studies and demonstrate the dataset task agreement. It can be seen that in a deeper look, we can see a connection between the auxiliary task and the downstream dataset. It can be seen that two patterns are formed in these two radar plots. This implies that these downstream datasets can be divided into two groups: hand-object interaction, which are something and Ego 4D, and general human action, which are Diving and EVA. More details can be found in the main paper. So the key takeaways of our work are that low-level scene annotation can be improved for presentation for solving downstream tasks. Synthetic video data can benefit a real-world video dataset using prompt learning while training all together, and that video transformer can capture useful information in a multitask manner, even if trained with multiple domain datasets. Thank you for listening, and please visit our project page.